Hi there, it's good to see you all again, and today will be the topic of soil physical properties. Let's check it out what we have here today. So the importance of studying of this topic is that the soil physical property normally will show us on how soils function in the ecosystem, and this happens because of all of the soil physical properties involved of mass and energy transport, exchange from one soil to another, or exchange from soil itself and to its environment surroundings. And can help us to manage with the most appropriate way to have a really good practice for soil itself. So soil physical properties can be applied to different fields like agriculture, especially all the important factors for plant growth like oxygen, water, nutrient availability. And in terms of environment, this can explain how pollutants can transport to soil or leaching from soil system to groundwater, and eventually will affect the food chain of human beings. And the last application is on engineer. So this can help in terms of irrigation system. So it's really important to study the physical property of soils. And this is the figure of soil, showing you that once you have take a look into the soil itself, you actually facing first of all soil physical properties like color, of course, the distribution among three different size of particles like sand, silt, and clay, and this is basically tell us the texture of that soil itself. Soil aggregate. This is arrangement among sand, silt, and clay that form up the micro aggregate size and become larger in size like macro soil aggregate. So that give you the unit of soil aggregate as representing the whole soil structure. And this is really important, especially the pore geometry and pore connection that give you a pathway for mass and energy to transport in the soil itself or exchange from soil to the environment surroundings. And next is the mass and volume relationship. Among these can give you a very popular soil physical indices like soil density and porosity. That it's good to know these properties of the soil that help us to manage the soil in a right way to keep the soil resource longer in terms of uses for the next generation as well. And soil aeration, of course, and water. So we get into the detail all of these items later on. First of all, soil color. Soil color is pretty easy in terms of ourselves, just know the soil at first, and this is probably the first feature or the first physical property that you probably are familiar with. That is the color, because that you can observe right away. Here is a photo of different type of soil that showing different colors. You can see that the color can range from really dark to yellow to pink or red or mixing among them. So this is totally completely different across the region and different weather as well. So let's check about why we got completely different in terms of soil color. The color change totally depend on the factor that involved. If you remember from previous lecture that showing you the components of soil, where you have the solid phase, half of the volume that consisting of a little bit of organic matter, and the major part will be the soil minerals. And you have another half of the volume that contain either air and water that kind of compensate to each other in terms of conquer the spaces in the soil system. This is where the soil color come from. It's might from the one factor or maybe combination of 2 or 3 factors together that reveal the soil color that we can observe in the field. For instance, organic matter, basically the humus, just a very important part that bring the soil color to black or brownish. But you gotta keep in mind that humus is a stable colloidal organic matter, so it won't got some decompose any further. And iron oxides and hydroxides of iron, of course, give you the red or yellow color. It totally depends on the degree of oxygen you have. Calcium magnesium carbonate that give the white color to the soil. Moisture itself, or just water, can change the color of the soil as well. So if you use some sort of a way to investigate the soil color, one of the things that you have to keep in mind that you have to standardize the moisture content first. Otherwise, in the same soil with different moisture content can give you different colors as well. So this is a statement that kind of generalize the idea of having different portion of soil components, like I showed before, that give you the statement like this: like the more organic matter, the darker the soil color. The darker color of soil, the higher of soil temperature. That's according to the how the soil itself can absorb the light much more when they have darker color. The darker color parent materials will develop into the dark soil. This is the very general statement that you might want to keep in mind. So basically, soil color is produced by the combination among humus, oxides, and maybe changing according to the moisture content. So once you see the soil has really dark color, you can't stereotype that can be from only from the organic matter, but it might come from something else that you have to specify further with some other information. To measure the soil color, because the color itself, once if someone say that my soil is in my backyard, the color is kind of brown, and some other people will say, yeah, I have a brown color too, but how come these two brown color soils can be compared in terms of the same system? So that way you can pass on the soil color with some sort of code that once you see the code, you know directly that, oh, you kind of have the same soil color. So there is a system that showing you with the 3D combination among hue, value, and chroma. With this system, one can tell their own code of soil color, so that it's really specific, so you can investigate that your soil color is the same or is different from others, and you can use some information after you knowing the soil color as well. Who think about the dominant spectral color, like the rainbow, where you have different colors, and value is actually the lightness and darkness from white to black. I get you more in detail in terms of individual this value. And chroma, the last one, is the purity of color itself or intensity. I give you some codes here where you can see that this is a 10YR 4x4. The red color part here, 10YR, is refer to hue, and the first 4 here is refers to value, and the last 4 here refer to chroma. So soil color are generally more ready to identify in moist state. So again, keep in mind that you have to make the soil become in moist state first before you measure with this system. Otherwise, you will miss something if the soil is too dry to measure. And here is the Munsell soil color chart, the system that I just explained. And this is big. This is come in the form of more like a book with the different pages that refer to different colors in 3D system, like hue, hue here. This is a hue information, and this is value, and this is chroma. And the book itself has the hole here. So if you have moist soil sample ready, you just bring to the behind this page and check or match the color with the standard color here, and you can state the soil color code right away. So it's pretty easy to use and identify your soil color. Hue is the dominant wavelength, like I said, it's like rainbow color. That's pretty easy to think about. The common soil hues range from red, red, and yellow for the most. Other hues like gray, beige, or green yellow, green, blue, or purple blue, we have just a few of that. So generally, this is the hue that involved in terms of soil system. It's just somewhere here. So basically from yellow to red, that's it. And the rest of the system could be applied for other stuff. Whatever that have color itself can use the same color system, but for soil we are focusing only on this part because that all the soil can have soil color. Value is the amount of light reflected. The number start from 0 to 10. Up 10, you can see that this is pure white, and pure black is gonna be 0 here. So this number can change from 0 to 10 once. Chroma is a concentration of the hue. Chroma can be up to 20, but it's not likely to exceed 8 for soil. So it's just somewhere here to 8. And you can see that number in the page of the Munsell color chart book as well here. This is where you can see the hue, value, and chroma in Munsell chart. That again, this is the hue, the location for hue. 7.5 YR up here, value, and this is chroma. See that? So once you identify, you match your soil color of the moist soil sample, you can see, you can read all hue, value, and chroma, and then you record that data. Again, dark color mostly from organic matter accumulation. Red color, of course, there is an accumulation of iron under plenty of oxygen. So that means you have a really good drainage system. Air can flow through the soil. So iron, the iron from here will be oxidized from. So you can see the color is in red, just like you have hemoglobin in your blood that forming a complex with oxygen, and that gives the red color of your blood. This is kind of same thing, but in soil you have some other iron complex. But again, this is a chemical reaction with the oxygen that gives the red soil color. In terms of yellow, the yellow color it comes from iron accumulation as well, but here you have less oxygen to involve. Gray color, it tells us that the accumulation of iron is you do have accumulation, but you have very poor in terms of oxygen. Once the soil gets in gray color, it tells us a lot of things, and one of the major things that you have to think about it is the drainage. So the soil itself probably has water locking, some kind of thing, so that give the soil or iron in the soil became more reducing form, like from iron 3 plus. After you have the soil in water locking system, the iron 3 plus will receive electron and became iron 2 plus, and that form can move faster than iron 3 plus, and that makes the iron in the soil kind of like subjective to move or leach away from the soil itself, and eventually the soil will show the color of the silicate clay, and that is gray color. So in this state you probably have lost a lot of iron already. So that's why once you you bring about water too much into the soil system and get them waterlogging long enough, or most of the iron oxides will change into iron 2 plus and then move away from the soil system, and then you see the color become gray. Not sometime actually, most of the time you can see different colors in one profile. Like in this case, you see that it's kind of brownish up top of soil surface, and you have gray color here in the middle, and you have yellow down there. So that tell you about the hydrology of the soil itself, like where you can see that there is some water loggings here, and up here you probably have enough oxygen, so that why you get iron oxide here, but you don't see much down here, something like that. Soil drainage basically refer to the length and duration when soil is saturated. This is not when you measure how fast a water drains from a soil. So if the soil take a really long time to be saturated, so that means the soil has really good drainage. That's the meaning of this. Gray color of soils shows or tells the drainage basically, and you have really bad drainage in that case. And again, it's come from iron that change from 3 plus to 2 plus according to receiving the electron in waterlogging system. The facts about soil color: again, iron oxides that give you red, yellow, or light brown color. Organic matter give you dark brown or black color. Low value, it means you have you you can guess that you probably have a lot of organic matter once you have low value. Soil color is a useful feature to soil hydrology, like I said, that you can tell the story about how soil can drain water. If the soil matrix is a uniform color, it means you have the same color throughout the profile, and you see the color is high chroma, at least above 2, so that soil is typically well drained, and that is in the oxidizing condition. They have a lot of oxygen. This is some sort of feature models in terms of color. Like here, these are not the predominant metric color of the soil, because the major matrix color is gray, right? But then you have the yellowish here, and that is the Mottles, you said. The redoximorphic features are addition or depletion of iron and manganese that caused by the redox reaction. So receive or lose electron in the system, and that involved in terms of iron compounds anyway. The second topics here will be soil texture. Soil texture is the particle size distribution, as I mentioned earlier, that this is the distribution among sand-silt-clay. And here we talk just this part. Soil texture refer to soil mineral component, just this part. So that means in step or procedure that identify the soil texture, we actually remove the organic matter out. So soil texture is really important, of course, in terms of physical properties. But if you interpret the result according to the soil texture and then bring that result to manage something, I think you probably miss some information, because soil texture involve only soil mineral part. They don't do anything with organic matter. So we have to keep in mind that soil particle size distribution or soil texture only involve here soil mineral. So once you need to interpret the data in terms of soil behavior and whatever that relevant to soil texture itself, it can be misleading as well. So you have to have more information to set up some sort of agenda to manage the soil system. But I'd like you to take a look here, like what is the meaning of soil particle size distribution. So basically the system that we use, we have more than these two. The first column is the USDA, the US Department of Agriculture, and the second column here is the International Society of Soil Science, they have different system to identify sand-silt-clay. But anyway, you can see that in Thailand we normally use USDA. So the class that you are watching right now is also rely on USDA system, where you have sand particle size in the range of 0.05 to 2 millimeter, and silt it's in this range from 0.002 to 0.05, and for clay particle is supposed to um, less less than 2 micron basically. You can see that different system have just this spot different. Basically, the silt particle will be different among the different system. I just want you guys to keep in mind that this is really important to remember. This is good number to remember for soil physical properties. So everything that less than 2 micron we consider as a clay size particle, and that affects a lot of chemical and physical properties of the soil itself. So at least you can identify the size of the soil particle once it comes to individual particle. And this is a relative size fraction showing you that how big of sand could be compared with silt and clay. But keep in mind that this is not a real shape of the soil particles. Like clay, the shape of the clay particle, especially once that clay size particle is clay minerals, it would be something more like sheets in shape, not a dot or a sphere like this. But this photo giving you an idea that what is the relative size among sand-silt-clay that you can see. For any kind of particles that greater than 2 millimeter in size, we consider as the gravel. So once we talk about the fine earth size fraction, we refer something that less than 2 millimeter and downstream of that. This is Sand-Silt-Clay Visualization. The gravel, sand, and silt, the shape pretty much almost like sphere. So you can assume when you do some sort of modeling or whatever that care about shape of the soil particle, they especially sand and silt is more like sphere. But for clay, this is invisible at this scale, so you have to use some sort of electron microscope to visualize, see how they look like. In this case, this is a kaolinite, one type of clay minerals, and this is really typical in Thailand that have this sort of clay mineral in clay size fraction. But you have to use some sort of equipment or instrument to check through the shape or the size of the particle. So of course, sand may be seen with the naked eyes, silt may be seen with a good microscope, and clay you only be seen with an electron microscope with the high energy. So in terms of mineralogy, again, clay, it usually are the clay in this mean is the size reference. This is the clay size particle. So the minerals in this fraction mostly are secondary minerals. We talk about the primary and secondary minerals later on. And you have clay minerals, of course, and some other iron oxide. This pretty much found in this clay size fraction. Now get back to here. The sand fraction is the biggest size fraction here, generally made up of quartz. So you don't actually see a lot of clay minerals in this size fraction. The silt fraction is in between sand and clay. Most of the time you will see a lot of quartz as well, and some other primary minerals like feldspar as well. Don't be confused about clay, because you can talk totally different stuff when you talk about clay. Clay is a size fraction of the soil. Like in the case of soil physical property, most of the time we refer to clay size fraction or clay size particle. Second, clay is a texture class name. So this is a texture name of the soil. When you talk about clay soils, of course you probably have a lot of clay fraction or clay size particle, but this is soil texture. And the last one, clay is a class of minerals. That is solely clay minerals. Yeah. So think about this, like if we talk about clay minerals, that clay minerals, if you have a lot, it's probably cause you have a texture of clay, right? And you probably have a lot clay size particle in clay fraction as well. But you keep it separately and understand that you can talk about clay with three different meanings. So be careful. Again, the soil texture. Soil texture is not um, is it's not something about organic matter at all. So make sure that you understand this statement, because once you say the soil texture is clay, loamy, sand, or sandy loam, or whatever, you just talk only a part of mineral or inorganic matter. So this is not something to do with organic matter at all. But if the behavior of the soil itself is supposed to involve with organic matter, then you can have just soil texture to interpret the result. All right, and the soil texture, basically, the literature out there report three separate sand-silt-clay, and this proportion must be 100 of total. Otherwise, you can't use the soil textural classes. So make sure that you understand this soil textural class. I guess you probably have some experience in the lab to check your unknown sample, identify them, like how much of clay, silt, and sand portion you have, and then you can use this triangle to identify the soil textural classes. So you can see that we have sand, start from here, 0 to 100 here. You have silt here, start from 0 here, and then to 100 here. And you have axis of clay here, start from here, 0, and up top here, 100. And you have 12 major different soil textural classes here, that when you have the number that sum up as 100, see. For instance here, suppose you have something like this. I like to leave some sort of question here that if you have a percent of individual particle like sand-silt-clay equally, like 33.33, something like that, but they're all equal, what kind of soil texture you will get? That's the question. What kind of texture that you will get? You're supposed to get because you have all of them equal, right? Are you supposing to get a loam soil, or you're gonna get clay loam instead? Just check that out, and we talk about that in the class as well. To analyze the particles size, you have to sieve out the coarse particle that larger than 2 millimeter from the fine particles that less than 2 millimeter. That's where we started to identify the particle size. Remove organic matter with the hydrogen peroxide. This is what I said earlier, that soil texture is nothing to do with organic matter. We remove them out of the system. We also disperse the soil particle with a dispersing agent, and that called sodium hexamethophosphate, and this stuff can keep the soil sample individually. They just separate from each other, especially the clay size particle. And we have to use Stokes law to apply in this problem to identify the particle size. And Stokes law is nothing but the relationship between particle size and settling time. And here's how it looks like. Once you apply Stokes law, this is a function of velocity. When the particle sink down to the bottom of your container that containing the liquid medium as well. So basically this tells us that once you have different size of soil particle, that ready up here you have let's say this is clay, the black dot is clay, and the red dot is silt, and the blue big dot is a sand particle. So once you have everything mixed together, and then you start let them settling out, and you have a certain distance here, which is the uh, s in length. You can apply any number here anyway, so you know that what the number for the s here. And once you start doing this sediment experiment, you see that I'll go back here one more time. You can see that the biggest particle move fastest, right? Again, one more time. See, sand, and leave you silt and clay hanging out here. So here you have to separate again. Let's say you probably have less than 1 minute to precipitate out sand, and you have to wait a little bit longer for silt, maybe up to 2 hours, something like that, and the silt can precipitate out. So you can measure the mass of clay at that time, and then you can separate sand and silt, and then you can have the proportion in terms of percentage. The way to quantify the amount of sand-silt-clay actually have more than this, but the two major one is the hydrometer and the pipette method. The hydrometer ones, you actually measure the density of particle suspension. So if you know the density here, basically is mass by volume, and if you know the total volume, you can calculate for the mass of the particle that you're interested in. But for pipette method, you just maybe what should I say? Just collect the suspension up here at the time that you know that is the time for silt or clay that's hanging out here. So that way you can dry up the suspension and then leave you just the particle that you're interested. And finally, you can separate sand, silt, and clay fraction, and you can make a percentage. And once you sum them up, you get 100% of all different soil particle size. And here, for instance, you have sand 40, silt 30, and clay 30. You got somewhere here. See that? Sand 40. This is sand axis, and this is 40. Draw a line up here, right? Silt 30, silt here, and this is 30 down here. And the last axis is clay. You got 30 as well. This 30. You see that all three lines come across to each other, and that is the point where the soil texture falling into the clay loam region. So you can identify that the first one is clay loam, and the second one is loam, and the last one sand 60, silt 30, and clay 10. That you get sandy loam. I like to leave one more question here besides what I ever just said few minutes ago. You can see that there is a boundary between all of these soil textural classes. If you have the number of sand, silt, clay just falling into the boundary for some reason, like in one case you have just right here, just like here. So that means you have to pick one of these texture. You're going to go for a clay or clay loam, and what's the reason behind? All right, or you got something right here. See that? It could be clay, silty clay, silty clay loam, or clay loam. Which one you're gonna pick? And that will be something that you have to have a reason behind that as well. So I'll ask you this question again, and hopefully that you can answer that question to the Google Classroom as well. So that way we can interact with the answer and try to come up with the idea of separate this texture or identify this texture right away once you have something falling into the boundary line. Okay, 2 questions. In the field, we also have the method that you can check the soil texture as well, because previously you have to do experiment like sediment experiment to separate the soil particle fraction, but in the field you can also do the method as well. And this is of course less quantitative, but it's really easy and pretty common for field work. We actually based on the sand, silt, and clay that have their own properties. Like sand, you have roughness or grittiness, and it can tell once you have the particles a lot enough with water, and then you just move around like this, you can feel the roughness of particle itself. That's according to the sand particle. Smoothness is still, you can tell that it's really fine in texture, but then you didn't feel like sticky like clay, you know, it's just smooth like silt, like silk, and we call them silk of course, but it's kind of the same like silk as well, because it's really smooth. And I bet that you will be able to check silk particle in the lab for sure. And thickness of course for clay. So this is the behavior among these three soil particle size. So you can use this behavior to identify. And there will be a demonstration of this in the lab section. Soil texture is totally affects the property and management of soil, even they not something to do with organic matter, but it's good to know. The smaller particle size basically give you the greater of total surface area of a given volume of soil. So this is the word we call specific surface area. So with higher specific area, that means you probably have a lot of small particle size, like you have a lot of clay size particles, something like that, and that will give you a lot more ability to absorb water, to absorb some sort of chemical, or provide the space for chemical reaction more, and of course absorb nutrients that really important for plant growth. So the texture also affects the porosity of the soil as well. And porosity is tell us about the amount and size of pores as well, and plant available water holding capacity. The texture can tell, like if you have a lot of clay size particle, you tend to have a lot of soil that capable of water holding properties. Clay is very reactive and hold much water. That's the thing. And this is tell us about sand, silt, and clay. Sand give you few large pores, so you have low water holding, whereas clay have many fine pores and give you a high total water holding, but not all available to plant. In terms of silt, it's such a really good in terms of compared to completely sand or completely clay. This will give you some sort of loamy soil where you can meet the two good stuff for soil, like water holding, and also that water holding can release for plant to use as well. So the soil texture tells us a lot about the limitation and potential of the soils. Soil texture and management. Soil texture is generally determined by parent materials and weathering process as well. If you have a lot of clay in the soil's texture, it means that the soil you have is very high in terms of development, or went through a lot of weathering processes. That's why you have clay accumulation into the soil. Soil texture is modified by soil formation, of course, and soil texture cannot easily be changed, and this is really true unless you said like you have you just want to do some pot experiment. You have sand, you have silt, and then you just mix with the clay you like, and then it's pretty easy to mix them. How come you say that texture is something is not it's difficult to change? But actually that is for really tiny scale. It's just really specific to pot. But in terms of across the region scale, texture can change, uh, cannot change like that easily. So it's also we got to think about in terms of economics as well. So it's really expensive to add enough clay to change sandy soil to be a loamy soil, something like that, and it's not really practical in terms of theory. But anyway, we need to know soil texture for potential or limitation. Like when you have coarse texture soil like sand, loamy sand, something like this, you know that the limitation of this type of soil is low in holding water and nutrients, of course, but the soil itself have a very permeable. That means they have ability to transfer water and air, so the air flow very well in this case. So you can pick some sort of plant that fit well with the coarse texture, like you know, some sort of the camp plant, like for any kind of cactus that go very well in sandy soil, something like this, because they don't need a lot of water, they need a lot of air. That's pretty much. So you can pick the plant that matching the soil texture as well, to reduce the technology that you're going to use and reduce the cost of the plantation. For this type of soil, it will be less runoff, high infiltration, but you can see some compaction as well, even they're in coarse texture. So you got to be careful in terms of tillage for this type of soil as well. Fine texture, like clays, sandy clay and silty clay, this can hold a lot of water and nutrient, but sometimes they hold too tightly. They had very slow permeability, so the drainage is a problem for this type of soil. Unless you have, you know, clay in texture, but you have really good structure. We talk about to that specific soil some other time. But in this case, this is typical for clay, that you can see very slow infiltration. You know, take a lot of time to bring water from the top of soil surface through the soil profile and go deeper, or we call it percolation. And most of the time, you can see some sort of clay can be shrink when it's dry and swell when it's wet. So this can cause a lot of trouble once you grow plants. So it totally depends on the clay mineralogy as well. But you know that you have a lot of clay, and if that clay is the shrink and swell type of clay, then this phenomena will be happen. So you gotta know what kind of texture of soil you have, then you can manage in the way that support your plant. So for that theory, you see that the medium texture is something that we like to have, and that is loam, clay loam, sandy loam, and silt loam. This is a really good soil texture because it's not too coarse and too fine. It's just the right portion of sand-silt-clay. So this is normally perfect or very good or very appropriate for plant to grow or soil organism when you need both water and air. So this is this proportion of sand-silt-clay will provide both water and air enough, and you have enough large and small pores. So that means that, you know, air and water flow and holding within the soil can happen, and that subsidized for plant really good. So this is a typical soil texture that we like to have in terms of agriculture. But it depends on plant you grow as well, because some of the plant already picked their own soil texture. Like cactus, they probably like to be with the sandy soil for the most. Alright, I think I'm gonna stop right here, and then I'll come back again for the next clip that's explain about soil structure. And hope you guys can get a lot of information according to watching this video. And in the class we will discuss more about this item as well, and then we have some other activity to play that are relevant to this topic of soil physical properties. Alright, this clip is done. See you guys next time. Bye bye.